computer. And then you're not on right now, right? Because you're just, okay. I've got some cool demos to show you guys today. I'm guilty of always going like right into the tech and not really showing like what we're doing with this, but let me zoom in here. All right, so this is Pipeline Community Edition. This is our free thing here. We're picking up on stars, by the way. Oh, yeah, I should do some quick like Meetup stats here. So I think we're at, what, 9,500? Starting to see a lot more data scientists coming. This has been a big trend, a lot more GPU folks. We got a lot of hardware. We got some VC people back here. Yeah, they're right there. Yep. Yeah, I just call you VC guy, right? So beyond your best pitch, if anyone talks to you, just assume everything is a pitch. That's one thing I came to realize towards the end of last year when we were starting to do the fundraising stuff. So the big thing tonight, thanks to Brett. Yeah, Brett has been coming to the meetups for a while now, right? Like, when did you and I first meet? Was it at the IBM cognitive thing? Yeah. And you had just got like TensorFlow working on your like iPhone or something? Yeah, and that was, you spent like a week doing it. I was like, yeah, how'd that go? You're like, it was the worst week of my life, but it worked. Actually, yeah, I would really, at some point, it would be cool to have like a session on that. Maybe it's like a Saturday afternoon or something, and we just get people to get TensorFlow working on their iPhone. Let's see. Check in here. Yeah, so Brett offered to do this talk. He's been playing quite a bit with the Go stuff, and there's a Go board over there. That's pretty sweet. Thanks for bringing that. I saw that in the comments. Yeah, thank you, Thumbtack. 9,500. More details to come. I guess that's just me battling. We've got a couple more meetups coming up. Actually, I think the next one is March 1st. That'll be back at, I think it's back at Chartboost, which is a really cool space. I've been speaking at some Kubernetes meetups recently, and there's a ton of stuff going on there. There's a lot of overlap. There's Kubernetes plus TensorFlow, like a lot of Kubeflow is a new project out of Google. So if you guys are interested, we're starting to see more and more machine learning in those talks, which is really cool. I don't think I'm going to have time, of course, to talk about the estimator stuff. But I'm going to show you guys Community Edition, which is where I've been putting a lot of the estimator API for TensorFlow, right? Like a lot of examples and notebooks. And as you probably know, PipelineAI gets these models into production. That's our whole goal. I've been meeting quite a bit with the NVIDIA folks recently. We've been partnering with them on some of the Jetson stuff and getting Docker images with TensorFlow serving, working on these small devices. And like super low score times for like image recognition, object detection, things like that. So yeah, there's a lot of cool stuff happening there. Let's see. Okay, so I'm going to babble for a bit, and then Brett's going to speak. So let me go back to this. I basically spent like the last 3 days doing HTML and freaking JavaScript, so I'm going to share it with you guys. Yeah, so here you can click on this, train models. You can go right into, this is a free GPU that you guys can use. It's a shared environment, community style, so don't put anything super sensitive out there. Yeah, here's a way to actually deploy a model, scale it up from the notebook here. You could also fire up Tensor board from here. So we've got some people doing some training, some GPU training, things like that. I'm exposing Kubernetes. People have been having a good time with this. They've been killing pods and doing all kinds of fun stuff. So I appreciate that. They're being like my little chaos monkeys. And yeah, here we see a bunch of models being deployed. We see some of the dashboards I'm going to show in a sec. We see Tensor board. One super exciting thing is this create function. So I've been working with these guys from OpenFaaS, function as a service, powered by this project called OpenFaaS. Tomorrow is OpenFaaS Friday, or FaaS Friday. He's a guy out of London. He's gaining quite a bit of traction on this project. I think they're up to 8,000 stars. You know, I'm infatuated with stars. These VCs value them $1,500 per star. So 8,000 times 1,500. That guy right now is worth $12 million, according to VC money. So this is a way you can, like deploy. Yeah, he has this concept of a store. It's just like a place to go for like pre-existing Docker images, but these are like essentially functions, right? These are lambdas. I believe Oracle, the last couple months, purchased a company called FN or something like that. Yeah, there was a talk at Docker the other night. So there's a lot of this sort of build your own Lambda kind of stuff. And oh yeah, it looks like they added a bunch more here, even just last time I looked. But you could also add your own. And so pipeline, the Docker images that like we create from either the command line or from Jupyter, you can create Docker images with your TensorFlow models, with your XGBoost, with your scikit-learn. You just put the coordinates in here for your Docker, for like Docker Hub or for your like Docker registry. So here's one here. So this is one I can actually create live. I was just creating it, like sitting over there, where it's just a Python function that you know, could call other functions. So it's just like the start of kind of custom ensembles of these Python functions. This is a predict. So this is like a full pipeline, like TensorFlow serving, and this is MNIST. This is actually the model that's powering this little demo. So if we click this, boom, we get that. And this is the confidence, so that was a 2, and it looks like that's the highest. We can generate some more here, some traffic, and we should see some blipping going on down at the bottom here. Yeah, so this is kind of one view that, you know, shows all of the capabilities. And yeah, this is all open source stuff. This is yeah, all the pipeline stuff. Also, starting to see this more and more to make these models more consumable. These like REST endpoints, and is, you know, actually producing snippets of code that are like readily like usable here. So we have these curl commands. You could actually copy and paste this. I don't think the copy to clipboard actually works. We can do boom and get the result right there. We could also grab the Python code, which I put in the like Jupyter notebook here, and do the search there. So yeah, some like work around that. Also, yeah, we have a Slack channel now, which is like pretty cool. Also, yeah, I don't know if you guys have used Intercom. You probably see this annoying thing in the bottom right, like on every website now, because it's every Y Combinator company is doing this. But it's a super cool tool. You just set it up on your site, and you can engage with people on certain pages. So if they've made it so far into the page, it's a pretty cool tool. It's kind of like a little bit sort of in your face, but you can, you know, capture people at the moment that they're stuck. This is something at Databricks when I used to work back there that we had been talking about for years, which is putting this intercom thing inside of a notebook. And when people are starting to get errors and things like that, you could actually make some like suggestions and say, oh, you're having problems with the data frame API. Why don't you check out, you know, this kind of thing. So that's where we're moving here. The trick is getting this little guy to play nice with JupyterLab, which is kind of a beast of its own. You know, this is JupyterLab. It's a complete rewrite of the UI. They're finally in beta, by the way, in case you guys have been tracking this project. So this is, I think, the very latest. I know it's 2 versions behind, but this is all in the past week, basically. So yeah, there's a lot of sample notebooks here. Check out the community stuff. So I'm going to show you guys. Oh, and then, yeah, so you can come over here. You can actually make the like JSON call directly here, which I'll spare you those details, but you can copy in. Here we could actually take an image. So somebody, I don't even know who did this. I think it might have been the OpenFaaS creator guy, but if we grab an image, I'll grab my own GitHub avatar here. Take the URL. So this is all through the OpenFaaS stuff. Paste in. We're going to actually invoke this function with that image. And we get back like classification. So it thinks I'm a barracuda. A ball player, yeah, I'll take that. That's kind of cool. A sturgeon, yeah, that's nice. So yeah, so you can have fun with that. But the cool thing, of course, is that you can actually upload your own. One of the things I'm working on probably this weekend, next week, is the ability to paste in your own functions. In fact, back at this Jupyter notebook here, I actually have the start of it where that's where the ensemble function came from, which I just created sitting over there. Is this thing here. It's not really ensembling right now. It's just taking in when it gets. And but this was completely done through Jupyter. I took a snippet of code from a cell, created a function out of it, and then deployed it. And let's see. Hello, Thumbtack. Let's invoke it. Fingers crossed. And it's just spitting back out. Yeah, so one thing also that we've been working on is with these ensembles, people want to know which models were actually part of a prediction. And so we're right now just passing back the single most dominant model, but we will pass back a chain of models. So if there are ensembles going on here and certain ones have different weights, we're going to pass this back and show sort of a graph of who is involved in these predictions. Also, let's see. What's the other model? Yes, I was going to show the fact that you could actually send traffic. So there's a way to route traffic between different versions. I was trying to get the GPU version I cracked out earlier today. I was going to show GPU versus CPU. We have it now where you can add Kubernetes nodes that are just workers, and they just come up and they subscribe to the master and do training jobs, serving jobs. But yeah, each GPU you would incrementally add. Also, we have support now for the P3s, so the Volta V100s, which are screaming fast. Yeah, they're pretty good boxes. So I think that's it, kind of a quick thing. This was my tweet from last week that pretty much summarized what I worked on for FaaS Friday last week. FaaS Friday is coming up tomorrow. That's what I'm working on sitting over here, which will be actually creating functions from Jupyter, formalizing that. But this is one Jupyter notebook full of pretty much everything possible. It's got Netflix open source, TensorFlow, TensorFlow serving, Prometheus, the NVIDIA Volta V100s. I was actually doing global peering here between the Oregon region from Amazon with their Volta V100s and Ireland. So yeah, I had that working, which I broke earlier today. And then all the Kubernetes stuff and proof that it's actually using the GPUs. So. All right, that was a whirlwind update. And Brett, are you ready? All right. Yeah, any questions, by the way? I never asked for questions. Just talk to me later. Yeah, plus I'm sick and I can't hear anything out of this ear. So hopefully I'm not shouting at you. Can you join the thingy? And then here's that thing. Do you even have a... Oh, you do have an audio jack? Wow. Yeah, Brett's got the new Mac, so everything's always a challenge. And then just share your screen and zoom in.
Testing 1, 2, 3. This is good. Yeah.
Louder.
Louder. Okay. Everybody in the background good back there? Okay, thank you. Hello. Just this slide. Okay. I'd like to thank you all for coming tonight. I'd like to thank Thumbtack for hosting us and Chris for, oh, sorry, we get the screen sharing working.
Oh, yeah. Can you share it? And join the audio on that device. Oh, now let me unmute you.
Oops. Okay. Okay.
It's good.
Okay. Yeah, I'd like to thank you all for showing up. I'd like to thank Chris for loading his soapbox for us, and then Thumbtack for hosting us. First, start with showing hands. Who here works with TensorFlow just in any capacity whatsoever? Okay. Who here has worked with like neural networks in any form? Okay. And then who here has ever played a game of Go? Okay. Go. Yeah, my background, I used to play a lot of chess, and I went back to school and took some AI classes, and Professor Chang let me study and basically write GoBots for a couple of semesters. This was a little while back, so there's new stuff that happened back then, but that's kind of how I got into this. And so I've been watching the AlphaGo stuff last year too. It's like, it's just very interesting to me. We'll cover a fair amount of material, so at the end we can do some Q&A if you guys want, but I'm just going to try to go through as much as possible, as fast as possible. So here we go. So we're going to do a super fast introduction to Go, overview of the rules. Then we'll look at how you can combine an algorithm called UCT with random rollouts to produce Monte Carlo tree search, which is the basis of all the modern approaches to this game. From there, we'll look at how they combine Monte Carlo tree search with policy and value networks to produce the AlphaGo series of engines. And then from there, last year, they extracted the policy and value portions and added self-play to produce AlphaGo Zero, which is, you probably heard about that one. And then a couple months ago, in December of 2017, they released AlphaZero, which is basically AlphaGo Zero without the Go knowledge, which is just sort of a general purpose AI algorithm that you can apply to other problems. And then we'll do a very quick demo of AlphaZero at the end. All right. You've never seen a Go board before. This is what it looks like. The basic objective is to fill up as many squares with your stones while your opponent's trying to do the same thing. You can capture stones as well. The origins of Go is from Asia. There's arguments about where exactly it came from. It's about 2,500 years ago. The board is 19 by 19. For beginners and stuff, they'll play on smaller boards, but we'll just talk about the larger board for now. So you end up with 361 squares, and your goal is simply to, like I said, fill with stones. There's a couple of different scoring systems here, but the one we're going to focus on is called the Chinese scoring system. It can be thought of as nothing more than the number of squares that you have stones on at the end of the game, plus the number of stones that you've captured. The The first player to move and go is black, as opposed to white if you're from your chess. Moving first gives you a little bit of an advantage. So at the end of the game, black has some points subtracted from their score in order to equalize things. So this is called coning. Coning is a fractional value, so the actual score for like a 19 board is now 7, but they add another half a point. So the upshot of this is that there's no draws in Go. One side or another always wins. The game will last about 500 moves. So this gives it a state space complexity of somewhere around 1 times 10 to the 170th power. To try to put that in perspective, if you're familiar with chess, that's about 1 times 10 to the 50th. The number of atoms in the observable universe is somewhere around 1 times 10 to the 80th. So if you can imagine the universe for every atom in our universe, you're still slightly shy of the state space to go. So how do you deal with this problem? UCD is an algorithm that comes to us from mathematics and probability theory. It's called the multi-arm bandit problem, which is a fancy way to say, how do you win the most money from a room of slot machines given a certain number of quarters? There's a few different approaches to this thing, but the basic idea is that you want to explore a few different machines. You don't want to put all your quarters in one machine. And then you want to calculate the reward of the machine. So if you put a quarter on a machine and you win $10 on it on the first try, that's great, but you need to make sure that you're not putting all your money into that one machine. So the UCD algorithm actually doesn't try to give you the best strategy. It tries to give you the least worst strategy, or lose the least amount of money possible. But whenever we convert that into game theory, the least worst move is actually the best move, so to speak. The next improvement to the UCD algorithm was to combine with trees to produce UCT. And this is the basic, down at the bottom here, it's roughly the how the UCT exploration algorithm looks whenever it's applied in the game Go. So we have an initial game tree. We select a node to expand, so we want to put in a new move. We evaluate that move. We say, we think this move will win or lose. And then we go back up the tree and we update all the associated nodes. So in this example, this move looks like a win for black. So black would kind of want that. But that means that white's probably not going to play in this position in the move before, so white would decrease their value for their score. But that means that black would want to be going down this lane, so the next one up, and so on and so forth, to arrive at the original node. And then you start the whole process all over again. UCT is valid as an approach to this game, but the problem that they had when they were attempting to solve Go is simply the state space is so large. So this C part over here is really where the magic happens, because there's no real good heuristic for how to evaluate a particular Go position. So in 2009, approximately, they came up with random rollouts. The basic idea is that you take the current board state, and then you pick your candidate move, which comes to us from the UCT portion of the algorithm. And you alternate adding stones randomly to the board, completely randomly until both sides cannot play. Then you can score the board using the Chinese rules, which are easy to implement. So that gives you whether or not you think this move is going to win or lose for that thing. And then you can go backwards and update your game tree. So the combination of these two algorithms, UCT, which random rollouts, is called Monte Carlo tree search. And it can be proven to asymmetrically approach perfect play on a board. The only minor problem with this approach is that the universe is going to die or run out of heat first. But that's what mathematicians call an implementation problem. So this was roughly the state of the art as of about a decade ago. And there were many different approaches that were discussed to try and improve from here. But as you're probably all aware, what happened next was AlphaZero showed up. So Google and some other people found a way to improve upon the algorithm significantly. This is Lee Steele, who's like basically one of the last humans to ever be a computer in match right here. The basic approach of the AlphaZero series of engines, there's like 3 or 4 different engines in the papers, so we'll refer to the original one as AlphaZero Fan, and then there'll be 2 others here in a second. But this is taking out Monte Carlo tree search, but we add 2 improvements on top. First, we add a policy network. So we want to quickly make moves. The problem with the Monte Carlo tree search is that we're making random moves. So we might try a random bad move, think about it for a bunch, and discover it is a bad move. But ideally, we of course want to try good moves and then evaluate amongst them. The second trick that we add is we add a value network to predict whether or not we think a particular move is going to win or not. So if we can have cheaper predictions, we can explore more of the tree, even if our evaluation function is weaker. And then finally, once we have this value and policy networks together, we can still use our original Monte Carlo tree search to perform deeper evaluations needed. But hopefully these first stage steps have reduced our search space down to the much more promising areas. So how do we do this then? The policy network is constructed by taking about 150,000 human games and applying supervised learning with a CNN to basically make a policy network. The purpose of policy network is simply given an input position to predict what the next move would look like. What would a human do here? Once they build that network, they recombine it with the Monte Carlo tree search, and then they play more games. So now we have human and computer games together, and then they can rebuild their policy network again. So this is reinforcement learning. Ultimately, the end goal is to use the policy network to make moves really quickly. The first engine they made was able to predict like a human move in any position with about 55% accuracy, which is significantly better than the other engines of the field today. But moreover, he was able to make that prediction in 3 milliseconds. They then constructed a second engine, which doesn't necessarily have neural networks in it. It actually used a smaller set of patterns and a softmax function. But this this engine was able to make 24% accuracy, so it's less accurate, but it's able to make its predictions in about 2 microseconds. So in 2 microseconds, 1 out of 4 times, it can make what a human-looking move just given a situation. So this policy network alone, trained on human moves, can actually defeat a lot of engines, which is a fact that we'll come back to in a second, but just remember that. The second piece of the puzzle then was to construct a value network. The basic problem we're trying to solve is that from a given input state, can we predict who's going to win the game without actually performing our full Monte Carlo simulation? So for this, they built a different CNN, whose job is simply to give it an input position to predict what the winning probability percentage is. It's trained on the MSC between the prediction and then the outcome, and then it uses like a distance to the end of the game heuristic to balance the moves. The problem with this approach is that it overtrains the input games. And so the engine basically just ends up copying what human beings are doing. So in order to overcome this limitation, they relax the network. So if you think about a go board like this, you can turn the go board 90 degrees. The game is still the same, you're just looking at it from a different angle. So you can take the board and you can rotate it 4 times around, but you can also take the board and rotate it over itself. So you have 8 different ways that you can look at one game, but the moves will still be technically the same internally. So after they did that trick, they're able to construct a value network which is able to predict the expected win-loss ratio of the game without doing a full rollout. So this second network was about 15,000 times faster than the actual Monte Carlo tree search. So here are these pieces, as we'll see, and how they all fit together. our y-axis is like an ELO rating, which is roughly can be thought of as the strength of these various engines. Green here is Stan V, who was the first player to play against the AlphaZero in 2015 or so. So he was like one of the strongest people in Europe, just to give you a rough approximation of where a human would fit on this list. These little red ones over here are some other Go engines from that era. GNU Go over there is down there in the way at the bottom. It's actually one of the first engines to play this game from the late 80s or so, just as a historical tidbit. So on the far side then, we have basically the combinations of these different parts. At the very far side, we have the pure Monte Carlo tree search portion of AlphaGo. So the thing that's interesting to me about this is that the Monte Carlo tree search in AlphaGo is actually weaker than many of the other engines that it's competing with. For the next one then, going this way from the far side, we have the policy network. This is simply a convolutional neural network that's pretending to copy human games, and yet it's able to beat the Monte Carlo tree search just by virtue of copying what a human would do in a particular situation. And next we have the value network, which I would argue is weaker at evaluating positions, but it can evaluate a lot more, so it can find the right moves better than the Monte Carlo tree search. Next, we come over here and we begin to see the power of combining these two different approaches. So combining the Monte Carlo tree search with the value network, we're able to get about 500-point improvement in performance. By combining the value and policy networks, we get a little bit more. By combining policy and Monte Carlo tree search again, we get up to 2,500 or so. And then finally, we have the full-blown AlphaGo engine, which is the combination of these two parts together, nearly 3,000 ELO, and was able to beat FAN3 in this televised match they did in 2015. The third blue bar over this way from this side, if that makes sense, the combination of value policy networks is the one I would like you to look at, because next we're going to look at AlphaGo Zero. So AlphaGo Zero has basically what I think are a couple of important improvements upon this engine. But the biggest one is that you can input a particular position, and they use a single network which combines both the policy and value networks to predict both the best move and the winning odds of that move in any particular position, which we can then use just to build our game tree. So then the AlphaGo engine, because it can do this, we can then play games with itself. We can start out with a completely randomized initial state. We can train a new network to categorize the wins and losses and reduce the prediction error. And then we can evaluate our new network against the old one and pick the winner. We simply take this process in, repeat it about 700,000 times, and we arrive at natural level play. If you're interested in the innards of how AlphaGo Zero works, this is a very excellent infographic you can download off the internet. The sub-play and evaluate parts will go through a little bit more. The retraining network is important because that's how the actual training occurs at the neural network level. On the far side, we have our actual game state and how we input it into the engine. It starts off with 8 layers of black moves. The most recent move for black, and then the 7 before. And then the most recent move for white, the 7 before. And then at the bottom is a layer that's all black if you're trying to predict the black move, or all white if you're trying to predict the white move. So we have a 19 by 19 by 17 stack, and that's how we encapsulate our game state at any particular point in time. Next, we come over here. We take our initial stack of the input state, and we put it into a 3x3 convolutional layer and do a normalization step right over here at the bottom side. And then next, we go over here to the far right side, and we perform a similar process with 2 3x3 convolutional layers and array those, and then we have built up a residual block. If if you're familiar with residual networks. From there, basically, we have 40 of these blocks. And then at the top, we have two.
Just for power. Yes, don't mind me.
And then at the top, we have the two output nodes of this neural network. One is the value to output what we think this position is going to. The first one is the output, what the value of this position is. And then the second one over here on the far right side is to output the most likely move from a particular position. So what we think the most likely move is and what its winning odds are. So we take this whole network and flip it all the way back upside down. We can basically rebuild our UCT tree from before. But now we can simply, for each exploration step, we can simply use our same neural network to expand the policy and value nodes as we go. And at the end, we can train the whole thing using like a glorified, we'll say, simulated annealing style temperature schedule to make sure that we're not getting stuck in a local minimum while we're beginning our state space search. Yeah, you should download this infographic if you want to go deep into how all this works. So here we can see how this all works in real life. This is the graph that's on the Google website. But basically, the engine starts out. It's extremely, extremely weak. It's basically just making purely random moves. And then after a certain amount of training, it actually approaches the level of a raw beginner. But from there, it continues to improve until finally it's past 5,000 ELO points, which is beyond any human being that's ever played in any other engine that's ever been written. On the far side, we have the 2017 version of our graph from a picture from before. So the AlphaGo that we were discussing before is the farthest dark blue block at about 3,000 ELO. Then the next one over is the AlphaGo B, which beat the Zero. And then the next one is the AlphaGo Master. And then finally we have the AlphaGo Zero, which is even a little bit more. Now, part of the difference in the strength of these engines is due simply to advances in computer hardware. The AlphaGo fan was trained on approximately like 172 GPUs, like off-the-shelf stuff that perhaps you people have. AlphaGo Lee was trained on a cluster of 48 TPU1s. And then the AlphaGo Master and AlphaGo Zero are trained on boxes with 4 TPU2s, which is an internal Google hardware that only came out last year. I would like you to remember this gray one over here. This is just basically the raw policy network of the AlphaGo Zero engine. It's able just to play this without actually doing any thinking, so to speak. The AlphaGo Master and AlphaGo Zero are both built and trained on the same hardware, we'll say 4 TPU2s. And yet the AlphaGo Zero is able to be stronger. So how does it do that? It's a combination of two approaches. The first is that the other engine is trained using supervised learning on human games, right? So this first graph right here shows how the supervised learning actually very quickly learns from the games that it's shown, but it hits a wall, so to speak, and it can't improve past there. The reinforcement learning starts off slower, takes a lot longer to get to the same point, but is able to keep on going, sort of a rabbit or a horse in the hair style situation. What's interesting to me as well is in the middle graph is that you can see that the AlphaGo Zero engine actually is worse at predicting human moves because it gets into a different realm of understanding of where the game is at. This bottom one is the second part of what makes the difference between these two engines. is won by combining the two networks. So these four engines right here are showing the difference between building separate and value policy networks as opposed to combining them. So combining them produces a significant increase in strength. The second trick then is using ResNets as opposed to CNNs, because ResNets can allow you to train to a lower degree of error, so to speak. And so the bar graph, the ResNets, the amount of difference in error isn't very much, but it translates to over 1,000 points in performance once you actually build the engine. This is sort of these are some graphics sort of show the engine in various states and plays as it goes from being like a raw beginner to a master. At the beginning of the game, it's just sort of grabbing as close as you can. As the game progresses, it starts to branch out, play on the sides. And then finally, at the end, it's playing on both sides, and it has a global vision of the game, so to speak. The top column of this row, these are called consecutive, which is like opening positions in Go. So basically the game, this is a graph as well, showing training time versus how much the engine is using these openings. So basically it's rediscovering these well-known historical Go openings, learning to play them, using them in its games, and then learning to refute them, and then ultimately either keeping these openings or rejecting them based on how well it actually thinks it serves as a heuristic for the game as a whole. Okay, so this is basically how the combination of all these techniques together solves Go, more or less. But the question is, how can you apply this to a different problem or something that you might encounter outside of this domain? So in December of last year, Google released this paper, which was called AlphaZero. It's a generalized version of the AlphaZero approach, but it has no Go-specific knowledge. So you provide three things to this engine: a board state, a list of possible moves, and an evaluation function. And from there, it can generate policy and value networks via self-play. So basically, you can learn to play any game if you can input it as these three conditions. So they taught it to play Go as well. It plays well. It actually doesn't beat the AlphaZero engine, but it's comparable with, it's better than anything else out there, we'll put it that way. They taught it to play chess. It plays at a master level with just a few days of CPU time. And then the middle one is the one that's interesting to me. Shogi is a game from Japan. It's played on a 10x10 board. It has some slightly different, it's similar to chess, but pieces move in a slightly different way. It's not historically been well studied or well, it's not had a lot of interest just because it's not super well known outside of Japan. But they were actually able to train like a world champion level engine just by the same concept. Showing the engine how to play the game and then leaving it alone with a bunch of CPU time. All right. So, okay, that's right. So this is also interesting to me. So this is the AlphaZero engine teaching itself how to play chess. And these is basically it's reteaching itself centuries of opening theory in this game. So what's hilarious to me is that I played chess for a long time. For the last decade or so, I played the English opening, so I thought that was like the strongest opening, and that's the one that the bot likes. So many people who play black for chess like to play the Sicilian defense, and one of the arguments against the Sicilian defense is that it's basically the English opening, but one move behind. And so many people. So it's interesting that the engine actually learns the Sicilian, tries it, but rejects it, and doesn't actually play it very much. So that's just interesting. We'll apply AlphaZero to a slightly less, slightly smaller problem, so to speak. This is some code I got off the internet. Shared there is a student at Stanford, and he wrote AlphaZero bot to play the game of Othello. And then a Russian guy by the name of Evgeny Turin modified it to run tic-tac-toe. So for tic-tac-toe, the input is a board, which is just a 3x3 square. The moves, any open square is a legal move in tic-tac-toe. And then finally, if you have 3 in a row in any direction, that's your evaluation function. So we're going to run this very simple bot. It's going to play some games with itself. Then we'll train the neural network to recognize winners and minimize the losses. We'll evaluate the network, and then we'll repeat. So here goes. All right. So first we're going to play like 25 or 50 games, or 25 games here, against itself, using a randomly initialized network. Next, we're running on top of Keras and TensorFlow. So we're going to train our neural network on this. I decreased the number of epochs in Eugenie's code. So this is kind of dangerous because if you get it too low, it won't make legal moves, but hopefully this will work. We'll find out. All right, so now it's training the network, and now it's going to play the new network against the old network. And three, two, one. Okay, so our new model beat our old model. So we declared the new model the champion, and then we just start the whole process all the way over again. The problem is the number of games is going to start increasing, so the training time is going to decrease significantly as we go deeper. But we've trained a very basic bot to play the game of tic-tac-toe. And here's our neural network, just our state, so to speak. So now we can play the bot we just trained against an engine that's been, was trained properly. So it had like an hour or two CPU time. So we'll see how well it does. Okay, so we're going to have them play 100 games against each other. They're just firing back and forth with each other. Okay, so the first player was our well-trained engine, so to speak. It had plenty of time, so it actually plays the game perfectly. But our bot, which we just trained, was approximately a minute of CPU time there, managed to draw 40 games against that machine. So it didn't do great in the grand scheme of things, but the more time we give it, the better it will do. So next, we can. This is a tic-tac-toe board, et cetera, et cetera. So now this is with 3 squares. We can delete that and change it to 4, and then rerun our training script. And now, as you'll see, it takes longer to run each simulation. It will take longer to train each network. But now, if we let this run, it will take like a while to run, trust me. But we'll have generated a bot that can play tic-tac-toe on a 4x4 board. So now, I ran that already. So Here we are. Do we want to try to beat the machine at tic-tac-toe? Anybody want to pick a move? Any move? Or? Yeah?
0-0.
Okay. Keep on going.
3-1.
3-1. Did I do 2? Oops. Oh, sorry. Yeah, it's 3 down or and 0. Where do we go next? 2-2. One.
0-3.
0-3. Okay, yeah. Oops. Yeah. You guys have drawn the bottom, but yeah. Okay. So, yeah. Humanity slides for another day. Okay, so I'll do a brief recap of what we've seen. Monte Carlo tree search in the form of UCT plus rollouts solves Go, so to speak, but this approach doesn't scale. We can combine expert knowledge, which is just prior games, either human or computer, with value and policy networks, which is sort of an optimization, to surpass human players. But from there, we've seen how a single network, randomly initialized, can reach even greater performance just by self-play. And then ultimately, I would argue that this approach generalizes to other domains and is very human-like, so to speak. So what do I mean by that? So I'll ask you a question. What is AI? Let's first take, like, say, the negative view, which is like the Chinese room example. You'll say to me, Brad, it's cool you can train a computer playing tic-tac-toe, but I can play tic-tac-toe perfectly. As a matter of fact, I'm more than willing to play you all day. And I say, great, okay, let me give you a piece of paper, I'll make this move, what do you do? And we keep on doing this back and forth until we've written down every single possible tic-tac-toe game. But then I can take that stack of paper, right, and I can put it into a book, and I can give it to another person who doesn't even know how to play tic-tac-toe. And I can say, whatever you do, just open the book, find the position, and do whatever move it says to do next. For 4x4 tic-tac-toe, to continue that thread, we can construct another book. It's just an even bigger one. So if you look at the raw policy network of the AlphaZero engine, that's basically the book of the AlphaZero zero bot. We could print it out. It'd be incomprehensibly large, but in theory, we could print it out, and I'd have a book that I could give to any person in this room, and they could play Go simply by opening the book, finding the matching position, and making the next move. Moreover, you would be like a 3,000 level player, which means that you'd beat everybody in this room and you'd be competitive at the world level. So, if you think about the whole thing like this, then all we've really done is just very fancy, stimulus and response, right? Our bot, the book isn't intelligent. The person doesn't really understand what they're doing. They're just matching the position, right? So, if you take this, then all of our neural networks and stuff are just really a fancy compression algorithm, so to speak. I think this is kind of like a negative view of all this. So let me offer a different point of view. If we were to teach somebody to play these games, what would we do? Well, we give them a board, we teach them the rules, and we have them practice, which is basically all that we're letting the computer do. And moreover, what is the difference between a master level player and a beginner? The master knows what positions to seek out, they know what situations to avoid, and they know this because they have experience, because they've played lots and lots and lots of games. The master has the master and beginner both have the same board, the same possible moves, but over the course of the game, the difference will reveal itself. And so I'll leave you with a quote from Casablanca, who was like the world champ in chess about 100 years ago. A reporter allegedly asked him, Casablanca, how many moves ahead do you think? And he said, 1, but the right one. And at the risk of anthropomorphizing our Alfred robot, I think that if you could ask it that question, it would say that that answer is absolutely correct. So, that's all I have.
Any questions? Just shout them out.
If you're interested in studying, I would highly recommend you read these 4 papers by David Silver. He's the guy who did all this, not me. So, go. Good question.
I'm familiar with chess, and I understand movements, but I'm not a grandmaster. But that's played on 8x8 squares, and you have the shogi, which is played on 10x10. Under square, because the go, which is played on 19x19, is 51 square. So, the human being, yeah, or able to play chess, or shogi, or go, or the machine is going to take over.
Well, in all 3 of those domains, computers are better than human beings, and that day is past. Human beings will never be able to compete with machines. Sorry.
What was the question?
Oh, sorry. In the games of chess, shogi, and go, if human beings will be able to beat computers' answers. So, not anymore. Sorry.
So it seems to me that the difference between probably what the Go engine has been able to do versus what humans do is that it's explored more of the space. So typically, I imagine there's a sort of human bias with respect to the number of games that a professional sees, because humans kind of learn how the sort of state space that they explore when they play games. Whereas AlphaZero would have explored maybe a much larger space, and therefore it's able to outplay humans because it's seeing a much wider variation of games. So it seems in principle that potentially if humans kind of explore this sort of state space that the AlphaZero system is not, then maybe it's find wins in that state space that AlphaZero hasn't yet seen.
Yeah, I would, one, I would agree with what you're saying about, human instincts, or one of the limitations of supervised learning is basically overtraining to things humans think are important and not really the deeper game, we'll fix it that way. Kasparov, whenever he was playing, he tried to play weird positions and stuff, but since like 2000 or so, you just can't trick the computer with that anymore.
Would you be able to use the neural network algorithm to be able to determine what's inside the black box? If you know messages that are going in, coming out, and you have time and certain characteristics of the messages, could you set up a model and then have the neural network be able to deduce what's inside the black box without any migrations that happen? What would you
do? Can we figure out what's going on inside the machine? Is that what you're asking?
Exactly, like what are the steps involved? Once I gave more information. Like a really quick example, say if it's a big computer network, how many servers are in there? Like, are they pods? Is it a big server pod? Is it, say, decentralized network, peer-to-peer, that sort of thing?
how are they constructed? Is that what you're asking?
Yeah, based on the needs.
The AlphaZero engines are running on just a single instance of 4 TPUs, which is a new neural network architecture from Google. The AlphaZero things were run on a larger distributed network. They have basically a pod of TPU2s working together. So it's about 96 TPU2s working together. They gives you about 4 terabytes of working memory. So that's basically part of the trick, is that they have this gigantic working set, so to speak. And then that working set, I think, would be what you're asking about. That's what the actual, it goes to the machine or whatever is in there, wherever it is. Does that help?
Well, actually, I want to be able to use that based on message data. Messaging data. To be able to use what's inside the black box. That was just an example. Not, yes.
We can follow up. I'm sure as you explain it more clearly. Thank you.
We don't know what are the applications of stuff beyond.
Thank you. Beyond the the Go model that you built and all of the resources on the chess that you mentioned as well, where do you see applications in the real world of that work? I mean, I know you guys do a lot of natural language processing algorithms and machine learning as well, but that sounds more like an R&D kind of project. Is there something that can come out of it?
Sort of. I would argue that these games are sort of a special case. Because you have the games, because you have the state and whatnot, you can simulate it super fast. Whereas, for example, if you're like running image processing algorithms and whatnot, all this stuff inevitably becomes I/O bound, because you're trying to feed as many examples to the machine as possible. If the computer can generate the examples itself, basically that's kind of what's going on deep down inside with the CNN networks and whatnot. And so that's what basically allows the computer to just work with itself as opposed to actually having to hit an input. A number of improvements to TensorFlow and other things have come out of this, so if you're building on top of these platforms, you're sort of getting the benefits of all this research for free.
Is there plans to use a capsule network in the AlphaGo?
Well, capsule networks came out, and they're more oriented towards computer vision problems, but certainly all these fields are semi-related, image stuff uses ResNets now and everything else, so I'm sure somebody will find a way to combine these things at some point.
And then I have one more question. Other than it actually being reinforcement learning and needing a simulation to run, what are the limitations they found with using AlphaGo? Actually, sorry, AlphaZero.
What are the limitations?
Sorry, what did you say?
What would be the limitations?
I mean, did they find any games that they weren't able to master or get a high level?
If you're wanting a research project, basically you can go out and apply AlphaZero to new games, right? And it literally feels open right now. Like I said, there's people who play Othello, there's a few other different board games, tic-tac-toe, and people are trying, because basically if you have enough CPU time, you should be able to conquer games. But you have to get those free TPU credits from Google Cloud people.
Okay, thank you.
There's probably foosballs on that list. Limitations. Speaking of TPUs and TensorFlow, we're starting to see TPU-specific code that's creeping into the TensorFlow code base. So there's the estimator API, and there's like a TPU estimator that wraps your estimator. So that's kind of interesting. Have you seen any more TPU-specific stuff inside of TensorFlow when you're researching this?
No, I wouldn't say so. I think one of the TPUs is just that they have so much memory in their clusters. I think that's really what the real secret is to a lot of stuff, is that they're just able to work much larger data sets.
Gotcha. Okay. Yeah, I'm curious to see how that's going to roll in and become a common, so they don't have to actually use a special TPU version. Just kind of adds a little more mystery to these TPUs, right? Like what's going on. Yes, how many Russians are here, by the way? Like, yeah, this is the topic to bring Russian people out. Yeah, of course.
Yeah.
Oh, question. Yeah, I just did 23, and I'm part Russian.
So one of the things I've been looking at is how to apply this to security attacks, where, say, like a state in your address space is the goal of the game.
Okay.
Have you actually tried to map this thing to a physically fuzzing attacks or something like that?
No, but sounds interesting. We should try it.
Okay, you saw that answer coming.
This is all brand new as about a month ago. So.
Hi. So a couple of the board games you showed tonight, Go, chess, shogi, are pretty similar in terms of the spaces they can have. I've seen on Google's DeepMind they do a ton of like Atari games as well. I don't know if they sell it or something else they have, but where do you see like the next sort of realm that this goes into? Is it like, are they going to keep edging up the complexity of these games that they're going to compete in, or what?
Sure. The Atari games, that's more of a environment versus a player style thing. And then this is sort of a player against another player, or more specifically itself in this case. The key search algorithms and whatnot that are used in Atari are kind of similar to some of the stuff here, but it's a little bit, yeah. But I think the search algorithms are interesting for like what you were saying about with the security stuff, because you can train a bot to try and break out a network or whatever. This is very pure board game research, and it'll be a while before somebody can figure out how to apply it to other domains.
Questions, anyone? Oh yeah, special thanks to Antje from Germany over here, from MapR Germany. They're in town this week or next week. She was checking you all in. I put her to work. She's still on Dusseldorf time, right? So it's like 6 in the morning. So. Yeah, any other questions on this topic? Yeah, I do want to point out that Nate and Jen, like these guys have been here for 4 years or something. And I was commenting, there was something weird. I like, walked into a startup and I saw the same people 3 years later. I'm like, I just want to point out that that's pretty cool. This seems to be a good place to work. And Nate's really up on tech, and he encourages his team to be up on tech. So you guys are on Google for some stuff, BigQuery, and then Amazon for the serving side, TensorFlow, all the way to Spark 2.0, all that stuff. Good place to be. And you can get on the old like Twitter Wi-Fi, which I had to do, by the way, because it seems to only be allowing port 80 or something. There's a lot that seems to be some, but yeah, your guys' thing. So and I use all kinds of weird ports. So yeah, you can get on the old Twitter. Okay.
Only 5 seconds. Oh, sorry. Yeah, this is my website. If you want to know more about me, I mainly make mobile apps, or that's what I've been doing the past 5 to 10 years now. And we've been working a lot on making custom solutions for solving problems on device. So running computer vision networks and stuff that you can use on your phone. Back to what you were saying, I did a talk on CNNs for mobile devices last summer. If you were interested in that subject, you can go to my website and click on work or whatever and you can watch that. So that's all.
Yes, could you be interested in like a Saturday morning or something where you guys bring your phone? Is it possible to do this in 4 hours? To get TensorFlow working on to get that poet for TensorFlow?
If you precompile a bias, yeah, maybe. But yeah,
if like we provided like enough pre-built stuff, and then they just
yeah, basically, if you have the libraries pre-built, it's actually not too painful, and then you can retrain it to try and recognize whatever you like.
Is it using TensorFlow Lite now? Do they update it?
Sure. No, I can chat about that. The demo Chris is talking about is called TensorFlow for Mobile Posts. Basically, they walk you through retraining an inception network and then running it on an Android or iOS device using TensorFlow libraries on the device. Since then, there's been a couple of major improvements. The large one is what's called MobileNet. It's a paper came out of Google last April or so. And then with TensorFlow 1.4 last September, they released TensorFlow Lite, or sorry, 1.5, which was released in January. Sorry, that was when it was officially released. So it's a stripped down set of libraries. So basically, you can train a whole NES network and then run it on your device using the TensorFlow libraries on your device. The other approach that you can do is what I've been working with lately. It's called TF4ML. You can convert the MobileNet model, or well, basically any TensorFlow model, if your quantized graph has certain properties. You convert it into a core ML model and then just run it using the Apple hardware to get optimum performance on the device. And then Google has in Android N, I believe it is, or maybe it's they're now supporting neural network hardware on the device. And so we're now starting to see devices out in the real world which will support running neural networks fully accelerated in the real world. But yeah, that all makes sense. And yeah, that's what I've been doing all day for the last 6 months or so. So trying not to be too Asperger here.
Yeah, the TF Core ML, I thought that project would just like die as fast as it showed up. Is it really being maintained?
This is people working on it. I made it like it's a little bit dry arguments to it, but
yeah.
I think there's interest in Apple to keep it going.
Is like Apple actually support? I mean, it's not like an officially supported Core ML library.
No, I guess not. It's supported by Google. Apple recently released another tool called Create, and then that one should build. Yeah, it's sort of closer to like Sidekick if you're trying to build like more traditional models and run on the device.
In terms of deployment, do you see people using Docker images on these devices at all? Some of these edge devices?
Running Docker on the phone?
On the phone? Well, yeah, so I guess I haven't really seen it on the phone, but not like Jetson, I've seen it on some other edge devices. Is there a Docker, like, can you run Docker on like iOS? That'd be awesome.
I don't know, but I would imagine maybe you can get something around Android. But certainly what I've seen is like taking models, encapsulating little Docker packages, and then running iOS.
So there's a trend towards doing the inference on these devices. Is there like a backup? I like do it on, or are people trying to score on the server and then like it doesn't come back in time, so then they run in like a degraded state on the device or something?
No,
it's less accurate.
No. Basically, this is what they're doing, and basically a combination of approaches. You can run on a device and get very fast recognition. If you're running on a device, say you can run much larger photos and stuff, which should improve accuracy for certain problems. But then I'll still often like press the image down, send it off the server so that I can figure out what things are messing up with the model in the real world, and retrain my models and push it back down. Yeah.
And for these mobile devices, like they have limitations on the size of the models and things like that. Like you're down to the Apple Store, not allowing more than 100 meg. Like, is that a real limit? Is that an actual thing that you guys bump up against?
Yes, and that, like, for example, the inception model is like around 100 megabytes, but So you can quantize the extension models, like each down to 25 megabytes, which is shippable. Some of the movement models I've seen are like 10 to 20, that you can do good stuff with there. So, but then also you can like, silently download a file and run it locally. If you can, pre-make that, so to speak.
Yes, I went to MNIST this year, and there was quite a bit of talk about binary networks and really low precision, for like 3-bit, 4-bit, things like that. Are you seeing anything going towards?
Well,
there's 8-bit quantization, which is pretty common. Anything lower than that?
Well, something I've been messing with is, if you can make small models, then you can put multiple small models on the device. So you might run one to then decide which next network to apply to, which is, that's sort of the thing I've been messing with.
Are people running Spark on these devices? I was in Bangalore last year, and I kept getting people asking me, is there anyone in Silicon Valley doing this? And I was like, no, I don't think anyone. It was a famous Databricks blog post about getting it to run on the devices. It's like a joke. It was a April Fool's joke, it turns out.
One thing I saw a couple months ago was Intel pushed out Big DL. Yeah. And so you can do a fairly, you can do a bunch of neural network stuff just within Spark and then export files without even having to touch TensorFlow, so to speak. I think they're fairly
yeah. All right, so quick show of hand. Do we have time for this? Just a few more minutes? Sure, yeah. For the next couple topics, coming up, there's a few options. There's a buddy of mine from Redis Labs, right? They have these Redis modules, and now they have machine learning modules. And so, quick show of hands. Does that seem interesting? To be able to run machine learning on Redis, live, right? Yeah, we have the Russians over here. Perfect. Yeah. Everyone loves Redis. The other topic is the Spectre, that speculative execution, the big loophole, and then meltdown. Anyone want to hear more details about that? There's a really, so on that topic, actually, there's a really good talk by a Red Hat guy. I can't remember his name. I actually tweeted about it. So I tweet basically to myself so I can remember these links when I come along. But it's about an hour and a half long video, and this dude is on the scene, just dealing with the whole meltdown, and different ways and how Google approached it, and basically keep performance high but security tight. So that was another topic. And then, Big DL. That's what actually got me thinking about this. Does anyone care about Big DL? Anyone? One person? All right. So we probably won't cover that. I've had a couple requests for that, but I don't really know those really people in that space. Okay. Thanks for coming. Thanks, Thumbtack. We'll see you in 4 years.
Thank you for doing that. My name is Michael. I could go, but I know nothing about this. When I saw that, I'm like, I have to go. I have to go. I told you what's your
Hi. So, I was trying to give it the most general case. Actually, there's a model in detail, the chemistry that they have developed, which is but I think this way, kind of isolated. Say you can tell the number of times something has been copied through social media. For example, there's a bit of information I get on the massive stream of social media. So just making sure it's nothing like that. The message modified.
I'll ask you.
Or put a message through and get it like that. So that would be recipients on another context with copies. So if I were to actually
I'm curious.
there's
Meetup and it's kind of a problem.
put that into text or something.
Right, it's fine, yeah, because most of the time, over speakers,
Is there a library?
and you ask the speaker to basically show the slides. And that's you can also record the audio as you flip through the slides. And you have this kind of slide cast thing that we actually use audio track plus
Yeah, like
I guess it's fine. I guess.
Which parts of the whole right.
I can check real fast. STIKIT.
So,
Sorry, I'll find it. Here we go. I swear, yeah.
based on those principles.
Actually, it's a big office. They acquired a company. They're on now they're really
So there's new
stuff. Yeah, they had
red bar with right
Yeah, it's all over.
well, you're still not quite sure how this is working. When you start consistently
set up here, so using Zoom to and that's
Lila zero, sorry.
and also
And right here is
how many levels between you can download all people how many levels where you can consistently totally like 35
and like you can see like one thing I was keeping an eye on was like audio. In companies and meetups as well aren't like we have like a government information program called
and then you sort of click the slide or the prompt or anything like that. So you have service new website where you upload the slides, right? And then you got to present your as you're giving the prompt, you use that set to actually select that slide, and that's like sort of what oh my god. And then those you have like they're lightweight. Yeah, so you can export it to like YouTube or but actually it's like an audio stream plus
Oh yeah.
They're like 10 years. I haven't.
Well, I'm just thinking you can subset it and basically compound the difference.
Well, I think it's got like set up. Yeah. I'm also on the.
I guess I should do this in a collision where you choose the other. Yeah, I was going to say, guessing how much numerical precision you
Yeah.
So they're using.
Oh, okay. Oh, okay. Not the in-person one. Yeah, the library. Yeah, maybe like that. Yeah. I do one that's and that yeah, and then this year I'm starting off you sure you know that? It's like a workshop. Neural networks. We're gonna have all the just yeah, and then the code is right here. That's my last name. That's not just use I posted a couple of videos. It's gonna be down.
Go to my website.
Thank you again.
Yeah, right.
Right here.
Yeah.
This is a whole talk I did on convolutional neural networks.
It's gonna be all of us. So yeah, I did this a couple years ago. So I'm gonna tie all this technologies together. It's going to be talking about all this serverless stuff. And then at the very end, I know maybe oh, sorry. Like program. No, it's just a yeah.
Other than that, it's nice to have this small, not important stuff. But I'm very excited.
So I'm like, rolling, I was at Pete's. It's at 6:30. I like 3 people.
Right. For a while I was playing. Oh, this should be all in place. Yes, thank you very much for doing that. It's a couple different things.
Do you have any idea how many flops it is in terms of floating point multipliers that this, if you're using this TF and running on the flop, so you can. Yeah. That must be benchmark.
I love it. People start calling us numbers. I'm like,
Where is AI? It's great.
I believe that we actually.
Just like, no, sorry. Okay, so randomly, not random, off that topic. I was trying with my team today. Well, which I know this is also not your area of expertise, but dog. It sounds true, it's not probably people are really mad about today because we don't understand.
So you're just trying to see this thing.
Really?
So the thought of it, it's scared away. Oh yeah, that's a big deal.
No, it's nice. So, you know, Phil and Miller would like all of the team meetings. Like he's Phil came to ours, which is really great. And I asked the questions, and now I told him now that I have to trying to look at the solution. But it's an on-product team, how can we accomplish the problem? Because we typically do a unit that's like, it's our first team we're doing it, and not the goals. And he's a dog food, right? Obviously, those are like product, like we're so close to that. And so I presented most of my take on that, so I just like briefly mentioned today, like this is something that perhaps we could try to do better. But so what I'm going to ask, like Chaz has seen something like that. Is there anyone interested in like spearheading the go because learn about documentary, come back and teach us how to do it so we can bring to integration first. One thing Phil said, she's like, it's just hard. She's like, you can find out about it. And you get like 3 sentences in and it's like, I'm done. And so I told them next week we're all going to get together and I'll work again if we don't find ways. So could you be a person that I feel like whoever takes your goals with me, or is there someone we can? Yeah, Andrew. Oh, okay. Either meet or just meet with others and say like, see, this is how you do this, this is how you explain to people. And maybe we can break down this. Right. Yeah. Yeah.
I probably can't congratulate you first. Now they're also they're basically
yeah. Right, this is we know it's there, but then, yeah. Yeah. And I think like until like dog fooding, I think a lot of us do dog fooding is like a very specific thing, but it's like now there's different places you can dog food in. Fish food, you can do the puppy thing, you can do, or you can just use I mean, I need works me up for beta app. Still don't really know what I'm doing. You know what I'm saying? So there's all of these levels of like, if I do it there, what's the yeah. So okay, so maybe it's certainly not gonna happen until a couple weeks, but when I get someone to spearhead this project, maybe I'll reach out to you and you can like make the connections to the team. Just yeah.
So they weren't.
well, yeah.
Yeah. Right. Actually, I've seen it. And I think to like folks watching too, I think we don't always the non-practical people. We tend to use the excuse of like, I don't know what we're talking about, but like our perspective could be really beneficial because of that reason. So it should be more active. Yes. Okay. And I think like even just that piece, because that's what I am the same way. And but like knowing that like those kinds of stuff you can file, like those are like this one, it doesn't have to be like you hit a wall and something breaks. It's like it's just I remember filing it that way. So I was hiring somebody for us for I hated that this was like at least a year and a half ago. You would click into something and you would start typing, but you would never be in the text box. No. No, this is great. I quickly counted, but I'm not sure exactly where it says to be. So it's 5,000. Yeah, I think it's awesome. Out of 5 months, yeah.
I feel like we're going to start supporting like, just like sign up to like things that never go.
You're getting like, yeah.
Yeah, friends might have tried that. But
Like if you don't know somebody trying to get it's.
So that would be $12.5 million. Does that was hardware can that
That's okay. We can send you a list of that's helpful. Is it useful or not really?
tried using
Well, so in order to sign in, they have to send the APA, and then it's just set it. Yeah. And I have to make sure we set it up slightly because they ask people if they're interested for us to Thumbtack. They opt in and they have an email list. So we can at least show you it's like just
are you guys?
Yeah.
always. I'm gonna go take care of something. We're gonna finish this document conversation.
Yeah. So we really should be doing more of these talks,
Her job. Google is just
I think very like the forward driving just maybe like putting our responsibility about 600 in our daily like we're using it by like customers.
oh wow.
So
Yeah, I think trade.
$5 a terabyte of data is given. So we do a lot of work with aggregator data.
Yeah, there's
like high level tables that like this is so useful. We don't know anything about the data side, but they're just copying and pasting very nice software. And like I care about like most of customers and I want to know this like so basically we made a table for each entity at the time. What are our KPIs for that? Yeah. I've actually moved a lot of ours back to West Coast.
Oh, it's not.
It's probably like 40 soon it's coming. So we've been using Google Thumbs Up, but I think we realized like there's not everybody's
It's different to what you think.
I think we're going to have
yeah, but they catch them right away. It's fantastic. So they found every single thing, which is why it's like 10.1. Great talk. I don't know. It's still recording.
maybe talk about something.
Yeah. It's like you actually practice too and stuff. It's amazing. That's all.
I don't like standing. Always my fear is I get up there and my brain like farts and I'm just standing up there.
Yeah, I hate public speaking. I did my PhD at